Okay, today we have a video for champions. It's only for the best of the best, and we will go through super advanced geometry. Just being honest, it's the most beautiful problem in geometry that I have ever solved. It's very advanced, and if you are interested at geometry, if you want to participate at math competitions of high level, that's the way to go. You should solve problems like this. You will see very quickly that even the language that we use here during solution is super different from the language that you used to see at AMC or AME. Usually when you work at AMC, how the problem is solved. You introduce some variable, and after that you maybe use sine rule, cosine rule, maybe you can find some similar triangles, then you come up with an equation, you solve an equation, and the problem is solved. Usually, like normal geometry from advanced math competitions can't be solved like this. It's not about to find the length of some segment, it's about the relation between different objects. For example, in this problem, eventually we will have to show that the certain line passes through the center of the circle. You see, it's a relation between the line and the circle. And in some problems, you will have to show that several lines intersect at the same point. And what I greatly recommend you is only one book. You need only one book, not many videos, not many resources, only one super advanced book that will make you like super cool at geometry. So this one, I'm pretty sure that you can find it in the internet because I did without any problems. And of course, it has several chapters. All the necessary theory is provided. After that, some problems are solved. Later on, you are offered to solve problems by yourself. And it has a lot of problems from advanced math competitions like USAMO, like Junior Math Olympiad of US, and IMO, and so on and so on. And as you can see from Kazakhstan, from IMO, super advanced cool geometry, and all the necessary theory is provided. It's only about 400 pages long. However, even if you complete something like a half of this book, you will be super cool at geometry. Just, I mean, it's the level here is not even comparable with AMC and AME, but if you have just basic foundation, if you know what is a cyclic quadrilateral, similar triangles, you can solve problems like this. And it is the way to go if you want to improve. So let's go to our stuff. We have an acute angle triangle ABC, circumscribed circle, orange, and O is a center of circumscribed circle. We fix some point M on circumscribed circle, and we connect center of the circle O with points A, with vertices A, B, and C. Then you drop perpendiculars from point M to OC. Of course, you need to extend OC in this case, and you need to extend OA to drop the perpendicular from M to OA, and then you drop perpendicular from M to OB. You see, these blue lines are perpendiculars. So these Y, Z, X are projections of M onto these red lines, and therefore triangle XYZ is formed. You need to show that in center of this triangle XYZ belongs to the Simpson line of point M with respect to triangle ABC. What is a Simpson line of M with respect to triangle ABC? So you see here is like a purple line. It's a very simple thing. So let me provide you some theoretical stuff. So if you have a point M on circumscribed circle, you can drop perpendicular like this one on one side, this one on another side, and this one on the third side of triangle ABC. Basically, you drop perpendiculars, and the feet of these perpendiculars, these 3 points, they always belong to the same line, and it is called Simpson line of point M with respect to triangle ABC. It's not a complicated stuff, however, let's prove that it is really the case. So here, point M, 3 perpendiculars are dropped. Why these 3 points belong to the same line? So let's look. You can show it in many ways. For example, I draw here, this segment is purple, this one is red, because now I have no idea if it is the same line, so it's like 2 separate segments. If we can show that this angle is equal to this angle, then these are vertical angles if they're equal, and definitely it is like one line. So as you have here perpendiculars, obviously there is a great hint that there are cyclic quadrilaterals. For example, if you look at this quadrilateral, like this one, you have one angle of 90 degrees like this, and another angle of 90 degrees like this, and here is like a common hypotenuse. Obviously, it is a cyclic quadrilateral because these angles are equal. For example, this one is also a cyclic quadrilateral, but for another reason. Here, the sum of opposite angles is 180, and BM here will be a diameter. In another cyclic quadrilateral, MC will be a diameter. So let's use this fact for our advantage. Here, let's connect points B and M. They are connected. This angle, of course, should be equal to this angle, just because they like subtend the same arc here. So these angles are equal because we have cyclic quadrilateral. Okay, let's go to the next one. Here, this angle will be equal to another one. Let me connect, for example, these 2 points. This and this angle should be equal to this angle, once again, because we work in cyclic quadrilateral. So if we show that these 2 angles are equal, then these 2 angles are also equal. Well, it's very easy to notice a very simple thing. For example, here, if we if we add this part, we will get like a larger angle. So this angle and this angle. So how they formed? This angle with 2 lines, it is formed from this small angle, and we add this part, right? So let me mark it with another color. And this angle with 1 line is also formed if you take this small angle and add also this blue angle. In other words, if you show that this angle, big one, is equal to this big angle, therefore we can throw away this common part and we will get that this small angle is equal to this small angle, right? So if we show that this angle that is formed by these like 2 lines is equal to this one, therefore common part can be like taken away and these portions should be equal. But it's very easy to show why these large angles are equal. Well, if this angle is alpha, this is alpha. Let's look. Here we have a cyclic quadrilateral, this one. 2 opposite angles are 90 degrees. If it's alpha, then the opposite angle, this one, should be 180 minus alpha. It's about the angle that is marked with this like 2 arcs, right? And for example, if we look at another cyclic quadrilateral, ABMC, it's inscribed in our circle. Of course, if this one is alpha, the opposite angle is definitely 180 minus alpha. So these angles are definitely equal, and therefore these small angles are equal, and therefore these are vertical angles, and it is 1 line. So Simpson line, like, it is now you know what it's all about. So, and in this problem, we also, as you can see, we dropped perpendiculars from point M to the sides of our triangle. Purple line is drawn, and it passes exactly through the center of circumscribed circle of triangle XYZ. So we will show it in this problem, but before we go into advanced stuff, what you usually need to do is to like investigate what you have in your picture. It's super important, for example, to understand what triangle XYZ is about. And the reason is because you need to understand what triangle you work with. Here you have a lot of perpendiculars, and when you have perpendiculars like this, immediately you have an idea that probably you have a lot of cyclic quadrilaterals, and you will be able to get some angles. For example, if I drop perpendicular from point M to this line and from point M to this line, immediately I can tell that, for example, this point, this point, this point, and this point, they belong to like the same circle, because these 2 angles are 90 degrees, right? So there is a cyclic quadrilateral. For example, MXOZ is also a cyclic quadrilateral because the sum of opposite angles here is 90 degrees. And I can continue and continue. For example, this small quadrilateral is a cyclic quadrilateral. Again, sum of opposite angles is 90 degrees. And of course, you will use it for your own advantage. You will be able to mark some angles, and maybe we will be able to find precisely what are the angles of triangle XYZ in terms of the angles of triangle ABC, how they are connected. And in this case, it is the way to go. So let's work on the angles of triangle XYZ. It will be our next step. We will use precisely the same picture, and let's look closer. Let's find some angle of our purple triangle. For example, this one. We can find any others. We just start from this one. I don't see any cyclic quadrilateral here that contains this angle, really. So I don't see. Maybe you see on the picture. So, however, you can see that this angle is like a neighbor with these other angles. Maybe I can find others, because you see that sum of several angles here, sum of these 3 angles is 90 degrees. And if I know 2 of these, this, maybe I can find x. What about this angle? Well, this angle is obviously, it belongs to this cyclic quadrilateral XMYO. XMYO, opposite angles are 90 degrees, and I can add this diagonal here, and I can mark another angle here, which is equal to this one. Perfect. What about this angle? Can I find it? And is it easy to find it? Well, at the moment it's not clear for me, but let me mark maybe some other angle, for example, this one. So what about this one? It's also a part of a cyclic quadrilateral. Which one? XMZO. This angle equals to this angle. Okay, so I have this angle and this angle, which are precisely equal to ones that I marked here, and they belong to this triangle. Here you see, here is a point of intersection. Let me mark it as T. I have no idea what is like the precise value of each of these angles, but I know that the sum of these angles together with this angle is 180 degrees. So maybe if I find this angle, but how can I find this one? Well, this angle that I'm looking for, it's between the perpendicular from the point M and BO. Perpendicular from M and BO, and it looks very reasonable. It doesn't look difficult, because really, how can we find, for example, this angle? Well, we can look at this, for example, this right triangle here, and if we know, for example, this angle here, this one is the sum, this black angle is the sum of 90 and this angle. And this angle is simply between BO and CO. So this angle is, for example, alpha, and therefore this angle is 2 alpha, because it's the center of the circle, right? And it is inscribed angle 2 alpha. This one is 180 minus 2 alpha. Let me write it, 180 minus 2 alpha, this angle. So this angle, black one, is external angle for this triangle. It equals to the sum of 90 and this angle. So plus 90 is the black angle, and it equals precisely to 270 minus 2 alpha. 270 minus 2 alpha is our black angle. Okay, so it's equal to this one, and sum of two of these angles, it's just together with this angle, they give 180. So sum of two of these is 180 minus this angle. So we can write that this blue angle plus our orange angle, this sum equals 180 minus this angle, minus 270 minus 2 alpha, which is equal 2 alpha minus 90. So sum two of these angles is 2 alpha minus 90. Here we go to the sum of these two angles is 2 alpha minus 90, and together with our desired angle they give 90 degrees. So in order to find this one, we have to take 90 and subtract sum of two of these. So the angle that we need, this one, equals 90 minus this sum of this, minus 2 alpha minus 90, which is 180 minus 2 alpha. Perfect. So as you can see, this angle that we were looking for, it is 180 minus 2 alpha, where alpha is this angle. So maybe there's just a coincidence, maybe only one angle of this triangle can be expressed through alpha, or maybe through some, maybe other angles can't be expressed like this. Maybe, for example, this one can't be expressed through angle C or through the angle B. Let's look. For example, here we are looking at this angle. Well, it consists of a couple others. So it consists of this angle. And is it some angle in cyclic quadrilateral? Obviously it is. This one is the angle in quadrilateral ZMXO, and it's equal to this angle, right? Okay, so what about the other part? The other part, let me mark it, for example, like this. Is it the angle in some cyclic quadrilateral? And it obviously is. So let's look. So here is the foot of one perpendicular, foot of another perpendicular, and I see here another cyclic quadrilateral, which is like this, MYZO. So here you have 90 degree like this angle, and here you have 90 degree like this, MYZO, definitely cyclic quadrilateral, and therefore this one is equal to this one. And you can see we have a very convenient thing. So these angles here, you have exactly the same angles, and this angle is equal to this angle. And what is this angle? Well, it's a very easy to find. It's the angle between BO and AO. So again, this angle, if we mark C as gamma, this one is gamma, this one is 2 gamma, and this one adjacent angle is 180 minus 2 gamma. Therefore, this one is 180 minus 2 gamma. And you see, it's super convenient thing. Here we got that this angle, when we dropped perpendicular on OA, this angle turned out to be 180 minus 2A, okay? And when we drop perpendicular on OC, this angle turned out to be 180 minus 2 gamma, so 180 minus 2c. And this one, when we drop perpendicular on a 180 minus 2a, this one, when we drop perpendicular on OC, 180 minus 2c, and therefore this one, when we drop perpendicular on OB, it just inevitably has to be 180 minus 2b. Well, it just comes from the basic math. Look, for example, one angle of triangle is 180 minus 2 alpha. Let's mark it as alpha. Another angle of triangle is 180 minus 2 gamma. What would be the other angle of this triangle? Well, the sum of all angles should be 180. Well, if you find this angle, if you need to find, you subtract from 180 sum of these two angles, which is 360 minus 2 and then gamma plus alpha. Let's see how will it look. What is gamma plus alpha? Gamma plus alpha is simply 180 minus beta, because gamma, alpha, and beta are the angles of your triangle, and the sum of these angles is 180. So if you substitute here 180 minus beta, 360 cancels out, and you will have here simply 2 beta with plus sign. You will have 2 beta, and the remaining angle turns out to be 180 minus 2 beta. So our conclusion that this triangle XYZ has angles like 180 minus one angle of triangle, another one 180 minus another angle of triangle, and another one 180 minus third angle of triangle. And it's very easy to distinguish which angle we need to subtract. When we drop perpendicular on OB, this angle formed by this base of the perpendicular, the drop perpendicular on OB, therefore it will be 180 minus 2b. When we drop perpendicular on OC, it will be 180 minus 2c. So it's just the basic research that will help us in the future, because if you have an experience in geometry, do you recognize any other triangle related to triangle ABC that has the same angles, 180 minus 2 alpha, 180 minus 2 beta, and 180 minus 2 gamma? It's not very difficult to find such triangle. It's definitely an ortho triangle. Really, let's look at our triangle ABC. Let's drop altitudes here, 1, 2, and 3, so they intersect at the same point. Can you show that these feet of perpendiculars, they form this ortho triangle, and surprisingly ortho triangle has exactly the same angles as this triangle? Let's check it. So let's connect foots of perpendiculars like this one. For example, what about this angle alpha? For example, this one is alpha. It's very easy to see that, for example, this angle from this right triangle, this one, is 90 minus alpha. Okay, and what about another right triangle? Do we have some other, which is 90 minus alpha? Just look at the picture and you will see that you have a right triangle here, and this one is also 90 minus alpha. Okay, this small quadrilateral is a cyclic quadrilateral. The opposite angles are 90 degrees. Therefore, this one is also 90 minus alpha. It follows from this cyclic quadrilateral. And it is also a cyclic quadrilateral. if this is 90 minus alpha, therefore this one is 90 minus alpha. And therefore this angle in total is 180 minus 2 alpha. So as you can see, we have an amazing coincidence here, and of course we will use it in the future. So this angle is 180 minus 2 alpha, opposite to alpha. For example, if this angle is beta, then this one opposite will be 180 minus 2 beta, and so on. This one will be 180 minus 2 gamma. Also, you should notice very interesting thing, that this altitude in triangle, what it is for this ortho triangle? It's obviously an angle bisector. You see, it's angle bisector, and this one will be an angle bisector for this triangle, and this one is an angle bisector for this triangle. So this point, orthocenter, is an in-center, the center of inscribed circle for this ortho triangle, and this is an angle bisector, this angle bisector, and this angle bisector. It's also a very important thing, and we will use it to solve our problem. So let's maybe mark here some circle, and it will be I. So that's what we need here to know. The first fact that we should emphasize, our triangle XYZ is similar to the ortho triangle of our triangle ABC. Well, because they have all the same angles, right? So these are similar triangles. It will be our second step. So let's finally go to the solution of our problem. So we figured out that this triangle XYZ, it has exactly the same angles as ortho triangle of triangle ABC. So in other words, they're similar. The surprising fact will be that not only this triangle similar to ortho triangle, but they actually equal. They have the same sides, and we will show it right away. However, the proof will be surprising. In order to do it, we need to notice that here we have a perpendicular on a diameter, and if you extend this perpendicular like through x by the same distance, you will end up on a circle. Really, if for example I extend here mx like this by the same distance, so if this one equals this one, then this point is exactly on the circle. Well, it follows from very simple geometry, really. If you have a diameter here, if you take a point on the circle, I drop from this point m perpendicular. Let me drop perpendicular like this. If I extend this perpendicular by the same distance, I will end up on a circle. So, if I make homothety with center at M and scale factor 2, x will appear on the circle. Really, scale factor 2 means that this segment mx increases twice in length. So this point x1 will be on the circle. What will happen to z? Well, obviously, we can extend this one and by the same distance, and z will be again on the circle, because this is also a perpendicular on another diameter. This is also a perpendicular to y to another diameter, and y after homothety with center at m scale factor 2 will also appear on the circle. So this homothety transfers our triangle to this triangle on the circle, and of course these triangles are similar. This orange triangle is simply twice larger. It has exactly the same angles as our initial triangle. So let me just jump a little bit back in time, so not to spoil our original picture, but you understand what will happen. So our triangle after homothety will appear the triangle that is inscribed in our circle, in this big orange circle. So let me make a separate picture here, not to spoil the original one. So what will happen to triangle XYZ? We will have some new triangle here, and it will look like this. This one, and this one. So here we have some x1, here we have y1, it's an image of y, and here we have, for example, z1, it's the image of z. So we remember that the angle x1 is 180 minus 2 alpha, this z1 is 180, z is from the perpendicular, it was a perpendicular on OC, and therefore this angle was 180 minus 2 gamma, right? 180 minus 2c, 180 minus 2 gamma, and this one is 180 minus 2 beta. Okay, so this triangle is 2 times larger than our initial triangle, and it is inscribed in our circle with some radius r. Okay, and what about ortho triangle? Can we also make some homothety of our ortho triangle triangle such that this gomothety will transfer our ortho triangle onto our this circumscribed circle. Well, obviously, if you know basics of geometry, the very simple fact is the next one. If you take, for example, ortho center of your triangle, for example, it's somewhere here, and if you reflect this point symmetrically with respect to this segment, so this distance is the same, this image of this point belongs to circumscribed circle. So this point, if you take this foot of altitude and basically you make a homothety with center at H, orthocenter, this segment will increase in length like twice, and the image of this point will be this point, and it belongs to the circumscribed circle. We can even show it, there is no problem. So very simple thing, you have a circumscribed circle, let's draw a triangle, and let's mark an orthocenter. We need only to draw a couple of altitudes to define orthocenter. Why, if, for example, I take this orthocenter, and if I make a homothety with center at this point and scale factor 2, why this point will appear on the circle? For example, this point is T. Well, okay, so I had a segment XT. I make a homothety with scale factor 2, so I need to extend this one by the same distance. And why this one will be the image of T? Well, in order to show it, let's just forget about homothety and just extend this segment. So we extend, and this is also a 90-degree angle, and after extension, this altitude intersects circumscribed circle. Let's simply show that this segment inevitably has to be equal to this one. So this is a point of intersection, and let's connect this one, and we will use the properties of angles, because this angle is equal to this one. They subtend the same arc. Okay, and what's next? This angle is equal to this one, because you have this right triangle here and this right triangle. This is a common angle for this right triangle and for this right triangle, and therefore this angle is equal to this angle is equal to this angle. And now if you look at this triangle, what do you see? Here you have an angle bisector that is also an altitude. Therefore we have an isosceles triangle here. This side is equal to this side, and by the way, this one should be also a median, so it is also equal to this segment. So homothety with center at orthocenter brings this vertex of ortho triangle to the circumscribed circle. Therefore, if you consider all the ortho triangle like this, if you make homothety with scale factor 2 at orthocenter, and the image of this triangle will be a triangle that is 2 times larger, and it will be on the circumscribed circle. Okay, here I just made a way better picture. Purple triangle is twice larger than triangle XYZ. It's the image of this triangle when homothety with center at M and scale factor of 2 is performed, so we have this purple triangle. And if you look at ortho triangle, the image is this one, right? So when you perform homothety with center at orthocenter H, the ortho triangle becomes this one. And these two triangles, they have equal angles. You see, this one is equal to this one. It's very important to mark precisely which angles are equal. So this one is equal to this one is equal to this one, and this one is equal to this one. So what can we tell about these triangles? Well, they are definitely similar because they have the same angles, but on top of that, they inscribed in the same circle. Therefore, they have to be congruent, because you have a sine rule. The sine rule tells you that in any triangle, A over sine alpha equals 2r. So these triangles, they have this one, the same 2r, and they have sine alpha, the same, because they have same angles. Therefore, their sides has to be the same, no question about it. And precisely, the side, for example, C1A1 in the black triangle, it is opposite to this angle, so therefore, it has to be equal to the side Z X, because in the other triangle it is opposite to exactly the same angle, 180 minus 2 beta. So triangles have to be congruent. This one is equal to this one, opposite to 180 minus 2 alpha. This side has to be equal to this side. So this purple triangle is equal to the black triangle. Purple triangle is twice larger than this purple triangle, and black triangle is twice larger than ortho triangle. Well, it means that this ortho triangle should be equal to this purple triangle, because they are both like 2 times smaller, right? Each one, because it is the image after homothety of ortho triangle, and it is the image of our purple triangle. As soon as they are equal, each of them is twice larger than initial triangle, therefore ortho triangle is equal to this one. By the way, it can be a separate problem on geometry, pretty advanced one, right? So to show that this one is equal to the ortho triangle. So we will use it in the future, but it's very important to notice here important thing that will be the key for our solution. How to turn, for example, this purple triangle into this black triangle. If you look at the picture, you can solve it as a separate problem, not advanced at all, very simple. If you connect A and X, A1, X1, and if you draw perpendicular bisector to this segment, so this is perpendicular bisector, reflection of the purple triangle, if you reflect it with respect to this perpendicular bisector, this purple triangle will turn into this black triangle. Of course, X will go to A immediately, but besides that, Y will go to B and Z will go to C. But I don't have a perfect picture here, right? It's not like super precise, but if you have equal triangles that are located on the same circle, these angles are equal and other angles are not equal, like this one is equal to this one, but they have equal angles in this manner. This one is equal to this one and this one is equal to this one. So it's very important, the location of angles. In this case, you can reflect one triangle like this one with respect to this perpendicular bisector A1X, and it will turn into another triangle. So it's a very important thing. We will use it in the future to complete our solution. Great, but at the moment this is it. So we perform homothety with center at M and scale factor 2. The main thing, what happens to Simpson line? We know what happens to this triangle. Let's show that the Simpson line will turn into some other line, okay, which is like basically it will be double distance from the point M, but this line, the image of the Simpson line, will pass through the orthocenter of triangle ABC. It's a separate problem. We can consider it as a lemma. So in any triangle, if you have a Simpson line, if you perform homothety with center at M and scale factor 2, the Simpson line, its image after homothety, will pass through the orthocenter of triangle ABC. Okay, here is a separate, very simple picture for our problem. We want to show that if we perform homothety with center at M and scale factor 2, the Simpson line will turn into the line that passes through orthocenter. Perfect. So I want to uniquely define Simpson line. In order to do that, I need to drop just a couple of perpendiculars. I don't need all 3 of them. So Simpson line is here, orthocenter is here. So what we will show now, that if you connect H and M, these 2 points, then Simpson line divides this segment in half, so that this portion of this segment is equal to this segment. So it's a midpoint, and therefore if this point is a midpoint of this segment, after homothety with center at M and scale factor 2, this point will go into this point H, and the image of Simpson line, of course, will pass through H. If you want to solve this problem normally, in a beautiful way, we need to do like very unusual, very original steps. Sometimes in advanced geometry, something unusual, something not obvious, greatly simplifies the solution. For example, in this case, we'll have to make a reflection of point H with respect to this side, and we'll use the fact that orthocenter, after such reflection, it will go to circumscribed circle. So this point T is the reflection of orthocenter, and we will connect point T with point M, and we will also connect these 2 points. Well, looks like very not an obvious step at all. However, you will see that now the solution will be very, very simple. Let's look, for example, at this angle BTM. It subtends the arc BM, and another angle which is equal to this angle, obviously this one, it is MC, well, let's call it V. let's call it V, MCV. So these two angles are equal, and you can see here, for example, this angle is 90 degrees and this angle is just one arc, and here this angle is 90 degrees and it is one arc. So you have right triangles here. Of course they are similar, but what we need to notice that this angle is, if it's alpha, it's 90 minus alpha, then equal to this angle. Really, if it's alpha, it is 90 minus alpha. This angle equals to this one. However, here you have an isosceles triangle. This angle is equal to this one, and this angle is also equal to this one because they are vertical. So, and let's continue. Look, here this angle, it is an angle in a cyclic quadrilateral. This quadrilateral, you have two angles of 90 degrees, it is cyclic. So this is, for example, beta, the opposite is 180 minus beta, and the adjacent is beta. So this one is equal to this one. So here you have isosceles triangle. But what does it mean that here you have a right triangle? This one is a right triangle and this one is isosceles. Well, obviously this one has to be median. It's very easy to show, really. You have, for example, a right triangle here, and this one is isosceles. This angle is equal to this angle. What does it mean for us? Obviously this one is alpha, this one is alpha. From the right triangle, this one is 90 minus alpha. From the right triangle, if it's alpha, this is 90 minus alpha. However, this angle, external angle of this triangle, is 2 alpha, and therefore this one from this triangle, because the sum of all angles is 180, has to be 90 minus alpha. Therefore, this one has to be equal to this one. It is also an isosceles triangle. So if you have a configuration that in the right triangle you have an isosceles triangle like this, therefore it has to be a median. There is no other way. So it is a median. So this segment equals to this segment equals to this segment, and Simpson line divides this segment in half. And it's also very important for us that this one is parallel to Simpson line. Really, look, this angle is equal to this angle. If you consider this second, Simpson line is parallel to this line. It divides this line in half. Okay, so let's even extend this h, let's call it k, hk. So basically, we figured out everything we need. So this line is parallel to Simpson line. It divides this line in half. It means that it will also, Simpson line will divide in half any other line that looks like, for example, like this. Really, because here you have this triangle is similar to this triangle. Really, this line is parallel to this line, and their coefficient of proportionality is 2, because this one is twice smaller than this one. Well, of course, if you consider HM, also you will have the same situation. This triangle is similar to this triangle, and this side is twice smaller than this side. So HM is twice larger than this portion, so therefore it is a half, and this one is equal to this one. It is a very beautiful solution related to real geometry. The conclusion: if you perform homothety with center at M, scale factor 2, the Simpson line will turn into the line that passes through orthocenter. Okay, we have very few steps to go. Let me remind you that we started that we needed to show that this Simpson line passes through the in-center of our triangle. We already performed homothety with center at M and scale factor 2. We considered the image of our triangle, and now we know that the image of Simpson line will pass through the orthocenter of triangle ABC. So let's mark it on the picture. So somewhere here we have an orthocenter H, and the image of Simpson line, let me make it pronounced, I will mark it with a green color. So the image of Simpson line like this, it will pass through this orthocenter. Obviously, this green line is parallel to the purple line, because after homothety we have parallel lines. So, but what we would like to show that this image of Simpson line will pass through the in-center of this triangle, because this triangle is an image of this one. It would be ideal, really, if it is the case, the image of Simpson line passes through the in-center of the image of our triangle, then everything, basically, we showed everything we needed to know. Because after homothety, this one turns into this one. The in-center of this triangle is the image of in-center of this triangle, and if we show that the image of Simpson line passes through the in-center of this triangle, we can take this homothety back. We can make it back basically with a scale 1/2 at point M, and obviously it means that the original Simpson line has to pass through the in-center of this triangle. Do you understand what I mean? The image of Simpson line passes through the in-center of this triangle, which is image of the original triangle. Therefore, in the beginning, we had like everything as we need. So ideally, we would like to show that the image of Simpson line passes through the in-center here. So let's mark it here. What do we know now for sure? That it passes through orthocenter. Orthocenter is an in-center of orthotriangle. So here, if you draw orthotriangle, these altitudes are actually angle bisectors for orthotriangle, and it is an in-center for orthotriangle, and this black triangle that we have here, it is an image of orthotriangle when homothety with center at H and scale factor 2 is performed. So this one is 2 times larger than the orthotriangle. Obviously, if it is an in-center of orthotriangle after homothety, you can see at the picture, this one will still be the in-center of this black triangle. It's absolutely obvious. So H is still an in-center of this black triangle. So let's track our progress. We know now that Simpson line, this green line, the image of Simpson line passes through the in-center of this black triangle. Okay. However, we need to show that this green line also passes through the in-center of this purple triangle. Okay, so we know that it already passes through in-center of one triangle, black one, but we would like to show that it passes through the in-center of this purple triangle. In this case, the problem will be solved. Okay, so these triangles, this black triangle and this purple triangle, they have a symmetry with respect to this angle bisector. They have a symmetry with respect to this angle bisector. So if you reflect purple triangle with respect to this angle bisector, you will get this black triangle precisely. So it means that if you reflect this in-center H of the black triangle with respect to this orange line, you will get exactly in-center of your purple triangle. So it will be probably somewhere here. Once again, I don't have a great picture, but the meaning is the same. So if one triangle goes into another after symmetry, then the in-center goes into in-center, right? The center of circumscribed circle will go into the center of circumscribed circle. So H will go into I after the symmetry with respect to this line. What does it mean? It means that HI, this line, is perpendicular, is exactly perpendicular to this line. H will go into I. Let me make a normal line here, not like this. Okay, so H will go into I, and these points are symmetrical. However, we need to show that green line passes through both H and I. If it is the case, green line has to be also perpendicular. If it passes through H and I, we know that HI are like images, one of the other. If we want this green line passes through the in-center of this purple triangle, it already passes through H, then it means that it passes through two of these points, so it has to be perpendicular to this orange line. So it has to be perpendicular, and how can we show that it is perpendicular? Because if we show, this is it, the problem is solved. Because it already passes through H, then it has to pass through A, if this angle is 90 degrees, and the problem is solved. We can show that it is perpendicular to this orange line if we show that it is parallel to A1x. If we show that the image of the Simpson line is parallel to A1x, it is automatically perpendicular to this line. Well, really, because this angle is 90 degrees, it is a second, and so the problem is reduced to a very, very simple fact. We need to show that the image of the Simpson line is parallel to this one. What is the image of Simpson line? Image of this line is actually parallel to the original Simpson line. So if we show that original Simpson line is parallel to a1x, then everything is like solved, and we get the needed result. So our final step now is to show that our Simpson line is parallel to a1x when what is a? A is the image of 1 foot of an altitude. This foot of an altitude, we extended it by the same distance from the orthocenter. Do you remember there is a homothety? So A1 has a very simple meaning. It is an image of a foot of an altitude here. And what is x? X is the reflection of m with respect to this diameter. It also has very simple meaning. If we show now that our Simpson line is parallel to this line, this is it. Everything is done, and we have like a victory. I separated the picture into two parts. On the left side, I have only Simpson line, and I need to show that this Simpson line is parallel to a1x. It's a great idea, especially if you have some complicated geometry, to separate, because imagine if I needed to draw Simpson line in this picture. In this case, besides all of that, where I need to define a1 as this like extension of altitude x, also as a symmetrical point of m with respect to diameter. So besides these points, I would have to draw perpendicular like this, and to draw Simpson line, the picture would be overburdened with elements, and in this case, it's very difficult to see even simple things. So it's a great idea to separate it, and I will remind you, we need to show that this line is parallel to this line, and we will keep it super simple. We will just show that, for example, this Simpson line forms some angle with AC, and it will be exactly the same angle which line A1x forms with AC. So we will extend it, and we will show that the angle between this line and AC is exactly the angle between this line and AC. So let's start with Simpson line, because here we have super simple picture. We are interested at this angle. So this angle, well, it complements this angle to 90 degrees. So if this is alpha, it is 90 minus alpha. This alpha, it belongs to inscribed quadrilateral. So let's mark this one. So it is alpha. This one also alpha. And how is it related with this arc BM? If BM, we can call it, for example, epsilon. Let's call it epsilon. And alpha equals epsilon over 2. Really, because alpha is the half of this arc. Well, if we measure arc in degrees, alpha exactly is a half. And in this case, this angle that we're interested at equals 90 minus half of this arc. 90 minus half of this arc is the angle that we need here. So it is this one. Okay, so let's work with the angle between this line and this line. So here we remember the result. That's the angle we need. So let's extend AX in order to find the angle between AX and AC. We extend this blue line like this, and we extend this black line as well. Just for our convenience, we will extend both of them to get intersection of both with AC. So what angles are obviously easy to find here? Well, for example, if we look at this angle, we can call it, for example, theta. This theta is inscribed, and it is equal the half of MA. For example, if MA is, for example, omega, in this case, theta equals this arc omega over 2. Great. By the way, theta is also, here we have a vertical angle, which is equal, which equals theta. And this angle that we're interested at this one. the angle between blue and black line, is external angle for this small triangle. So this blue angle equals the sum of two other angles which are not adjacent to it. So it is equals theta plus this other angle. Okay, what is this other angle? How can we find it? Let's look at the picture. It's very simple to do. So now we look at this black line in total, and we need this this orange angle, right? Orange angle. So we have black line here, and you have this right triangle. This orange angle is 90 minus this angle. Really, because in the right triangle, these two angles, they give 90 degrees in total. But this angle is very easy to find. It's the center of circumscribed circle. And for example, if this one is beta, this one is 2 beta, and this one is 90 minus beta, because simply we have isosceles triangle here. This side is equal to this one. So if it's 2 beta, this one is 90 minus beta. And in the right triangle, this remaining angle should add up to 90. So this one has to be beta. Great. It means that this angle is actually equal to this angle. Beta, it's related to the vertex B always, right? So the angle that we are looking for, this blue angle, is the sum of theta and beta. Look at the picture. So this blue angle is the sum of theta and beta. By the way, theta is omega over 2. Let's go into arcs. Remember that here we can rewrite theta is omega, this arc, over 2, plus beta is this arc AC over 2. So let's emphasize what we have here. The angle between A1x and this black line is the sum of these half arcs, omega over 2, and this arc AC over 2, small arc AC over 2. And we want to show that this one is equal to this one. Let's write what we have here, just below this picture, that 90 minus epsilon over 2. By the way, this one is epsilon. So what we have, we want to show that 90 minus epsilon over 2 equals omega over 2 plus AC over 2. Let's leave 90 on the left side, and everything else will be on the right side. So I will rewrite it like this. I will write it like this one. So is it obvious that 90 equals epsilon over 2 plus omega over 2 plus this arc AC over 2? Pay attention at the picture, and you will see maybe in several seconds that it is really the case. Let's look at the intersection of this black chord and this black chord. This one and this one. Here you have 90-degree angle. It's a very simple theorem that this angle, 90 degree, it's a half sum of these two arcs. So 90 degree equals half of this arc. Oh, by the way, we have it here. And half of this arc, AC, we have it here. So this equality is definitely true because of this 90-degree angle. And therefore, this one is equal to this one. So this blue angle is equal to this blue angle. And therefore, Simpson line is parallel to this line, and because they intersect AC at equal angles. So these lines are parallel, and it concludes the solution of our problem.